Welcome to Math 2320. This is section 4.8. We're looking at Green's functions. So we need a little theory first as to how do we get to this thing called a Green's function. So supposing we have a second order differential equation here where we've sort of standardized it. The lead coefficient has nothing in front of it. The initial conditions are 0. So sometimes the solution to this, if it's a representative of a physical system, is called a rest solution. Now we've seen that we can solve it by variation of parameters, where we take the homogeneous solution and our particular solution is of the format u1 y1x plus u2 y2x. We did this in a previous section. We had the Wronskian, which was we took our fundamental solutions, y1 and y2, y1 prime, y2 prime. We did the determinant of it to find, and then we solved to figure out what was u1 and u2 prime. And they had these particular formats. So to get u1, we integrated from our initial condition to some particular x, and we did this for u2 as well. So my particular solution, if I put all of this stuff in, remember we had u1, y1, u2, y2, put all of that in and keep it in integral format, you see we've got this piece in here. Here's our driving function on the right hand side. The y1 is with respect to x, y2 is with respect to x, and y1 and y2 differ in terms of t. T is the thing that we are integrating over, that variable. So this particular thing is our Green's function, this capital G, which is a function of x and t. This is our Green's function. And so you can see our Green's function is an integral part in the particular solution. So here's the Green's function, which depended on the fundamental solutions, and here's our driving function on the right hand side. And so to make a few comments here, remember our full solution is a combination of the homogeneous solution and now the particular solution. So here in this case, this is our system response due to my initial conditions that are given in the system. And yp of x is the response, how the system is reacting to the particular driving function on the right hand side. So you see, we know this. It doesn't depend on the driving function. So you know all of these parts, and you can vary the driving function on the right hand side to see how the system responds to a particular driving function. Alright, so let's take a look. What does all this mean in practice? So we have our non-homogeneous problem here. We form the homogeneous equation. We get our quadratic equation that goes with this constant coefficient second order problem. I see it factors into m plus 1, m plus 1. So it has repeated roots of minus 1. So we know what the homogeneous solution looks like as c1 e to the minus x, c2 x, e to the minus x because it has a repeated root. Alright, so we'd like to see what does this Green's function look like. Alright, so first off, remember our Green's function is y1 of t, y2 of t, y2 of x, y1 of x, and the Wronskian on the bottom is not in terms of x but in terms of t. So here's our Wronskian. We fill in my fundamental solution e to the minus t and t e to the minus t. We need the first derivative, so I pick up a minus 1. The derivative here, I need to use the product rule. Alright, so to get the determinant, it's the downward diagonal minus the product of the upper diagonal. So here's e to the minus t times the thing we got from the product rule minus the other diagonal. Now the good news is minus t e to the minus 2t cancels the t e to the minus 2t. When you distribute e to the minus t times e to the minus t, the exponents add, and so you get e to the minus 2t. Alright, so now it's a question of filling things in for my Green's function. We have y1 of t, y2 of x, minus y2 of t, y1 of x. Alright, and on the bottom we have the Wronskian that we got. If you look at the top, what's in common you could factor out is e to the minus t, e to the minus x, leaving you x minus t. Now at that point, we have e to the minus t over e to the minus 2t. So the exponents subtract minus t minus a minus 2t. So e to the t plus 2t, giving me e to the t. Alright, so I've got e to the t, I've got this e to the minus x, and you can leave it like this as your Green's function. Or you could factor out the minus 1 to make the term x minus t appear in both places. Alright, in question 2. So in question 2, here's my particular differential equation. I form the homogeneous problem. We have our polynomial, our quadratic here to solve, factors into 4m minus 1, 4m minus 1. So I have repeated roots of 1/4. Alright, so that would give me my y1 and my y2. If I look at the Wronskian, alright, so here's our Wronskian, plugging in e to the 1/4 x, its derivative. Here we have our y2, its product rule. Calculate the derivative, calculate the determinant, downward diagonal minus the upward diagonal. Alright, and so we get what the Wronskian is. Now, I wrote it in this form. Normally we need, as you see, the Wronskian as a function of t, but in this case the problem asked us to find it in terms of x. Alright, so there's a slight difference here just because of the way the problem asked for it in terms of x, and not in terms of t. All right, so coming back down here. So now I'm looking for my Green's function. I fill in y1 of t, y2 of x, y2 of t, y1 of x. Again, look to see what's in common that factors out. I've got a e to the 1/4 t over e to the 1/2 t. Exponents subtract, giving me a minus 1/4 t. All right, at that point, if you remember, our original problem had this 16 in the front, but in terms of the theory that we developed, the lead coefficient should be a 1. And so I divide everything by 16, and so I get 1/16 my driving function. And so here is my Green's function. I take out, or I put over a common denominator, x minus t over 4. Here's the x minus t, and then here is my driving function, giving me my particular solution. All right, in question 3, we have our non-homogeneous problem. We form the homogeneous one, get the quadratic equation to solve. I get a repeated root as we had previously. I form the Wronskian in terms of t. All right, so simply fill things in, calculate their derivatives, a product rule, get the determinant. All right, clean it all up, see what cancels. We've got the 6t e to the 12t minus 6t e to the 12t cancels, giving me that the Wronskian is e to the 12t. Now you might ask yourself, all these times we're getting a Wronskian, it's never 0. And it is the denominator for my Green's function. Why is it never 0? Well, if you think about it a little bit, remember the Wronskian came from y1 and y2, which were our independent solutions, and the Wronskian is not 0. All right, so form the Green's function, again, just filling in terms of y1 and y2, in terms of t and x. As we've done in the previous problems, let's see what's in common. Take it out. All right, and now I've got a 6t over a 12t. So e to the minus 6t. All right, so I've got my Green's function. So my particular solution then is, I take my driving function, which is given here is e to the 6t. I've got all of this part, which is my Green's function. The e to the minus 6t times e to the positive 6t. When you combine those, you get e to the 0, which is 1. All right, so I'm integrating this with respect to t. All right, so I've got this first term, a lot of x's, but we're integrating with respect to t, and so it just all acts as a constant. And we're plugging in t equals 0, my initial condition, and up to t equals x. And so essentially I get x squared e to the 6x. This one in terms of t, the e to the 6x is a constant. From the t I get 1/2 t squared, and then I'm plugging in t equals x, t equals 0. Alright, so I get an x squared. And so finally, I've got a 1x squared e to the 6x minus 1/2 x squared e to the 6x, giving me a 1/2 x squared e to the 6x as my particular solution. And in question 4, let's see. I take my differential equation, form the homogeneous problem, get m squared minus m is 0. Doesn't have repeated roots here. My roots are 0 and 1. Alright, so I get for the homogeneous problem, it has this solution. And if I plug in my initial conditions, okay, so if I plug in 0, I get C1 plus C2 is 12. And if I calculate the first derivative, I get C2 e to the x. Plug in 0, e to the 0 is 1. And so I get C2 is 1. Well, because the sum has to be 12, C1 is 11. Alright, so here's my homogeneous part. I then go to solve for my particular solution. Well, first I need the Wronskian. Well, you might think, well, what is y1? Well, y1 was a constant. And the constant came from e to the 0, which is just 1. Derivative of 1 is 0. My second solution was e to the t. Derivative is e to the t. So the Wronskian is pretty easy. It's just e to the t. So now a question of finding the Green's function. Alright, so we plug in my y1. Alright, got y1, got y2, my y2 of x, my y1 of x. Alright, so if I split this up and cancel, here is my Green's function. So my particular solution is the integral from x0 to x, my Green's function times my driving function. Well, in this case, our driving function on the right-hand side is just a 1. So essentially, I'm just integrating my Green's function. Alright, so I'm going to split it into two integrals. E to the x is as a constant. So I'm simply integrating e to the minus t. So I get a minus e to the minus t. Plugging in t equals x and t equals 0. When I integrate this 1, I get a t. And again, filling in t equals x and t equals 0. Alright, so cleaning this up, I get a minus e to the minus x. T equals 0, I get a e to the 0. So I get 1 minus e to the minus x, and from this piece I get x. And so finally, distributing this in, I get e to the x, I get a minus 1. So all of this is my particular solution. And if you combine that with the homogeneous one and combine like terms, I've got 11 minus 1 is 10. I've got this minus x, and I've got a 1e to the x, another 1e to the x, so 2e to the x. So Green's function plays an important role in looking at how the driving function affects the system. For those of you eventually taking partial differential equations, you'll also see that Green's function plays a role there.